Welcome to AP Podcast 5.4. This is on gas stoichiometry. This stuff is for review for all of us, so I'm going to go fairly quickly. But like always, if you have any questions, don't hesitate to ask. Now, like all stoichiometry problems, the most important concept, of course, is the mole. And we want to make sure that we're doing all our problems by finding some moles. Now, two things typically happen in a gas stoichiometry problem. They might give you conditions that are standard temperature and pressure, which is really handy because if that's the case, then we get to use this nice little conversion right here, and that saves us a lot of trouble. However, if it's not under standard conditions, we'll use good old Pivnert to find some moles. So without further ado, let's get going on this problem. Now here we go. We've got a problem. Mercury can be produced by the following reaction, and you can see mercuric oxide heated up gives you mercury and oxygen. And we're going to find out what volume of oxygen. So the first thing I want to do is make sure my equation is balanced, and it doesn't look like this one is. There's 2 oxygen there, so I'm going to put a 2 right here. Now I have 2 mercury, so I need 2 mercury there. So now I have a balanced equation. So let's go ahead and do this problem. Now you've been with me long enough to know that what's the first thing you do in stoichiometry? And they all called out, find some moles. So we're going to find some moles. So I've got 4.10 grams of HCl, and 1 mole of that stuff weighs 216.59 grams. And so when I find my moles, I get 0.0189 moles. All right. Now, I found the moles of HCl, but we're looking for the volume of oxygen gas. So I've got to go mole ratio, right? So the mole ratio is for every 2 of these, I'm going to produce 1 of those. So 2 moles to 1 mole. And then I'm just going to save myself a step. Since the conditions are at STP, and right at this point I've got moles of O2, I'm just going to continue on. 1 mole of O2 at STP is 22.4 liters. Oops. And so if you work that out and check my calculation, you should get 0.212 liters. I'm running out of room. Okay, so there's the first gas law stoichiometry. Not too bad, a little blast from the past. Let's try the same problem, though, under a little bit different conditions. So now it's not at STP, and so we're going to go ahead and use Pivnert. Now, everything to this point is the same. For example, I still have to find moles, and I still have to do a mole ratio. However, at this point, I didn't show it. In my calculator, I would get 0. Here, let me use a different color. Help you out. I would get 0.0095. Oops. That's just a mess. Horrible. Horrible, horrible, horrible. Let's try it one more time. 0.0095 moles of O2. Now why that's important is because I have conditions that are not standard temperature and pressure, so I've got to use a Pivnert. So we're going to solve for volume, so V equals nRT over P, and my moles, as I just said, 0.0095. R is 0.0821 liter ATM mole Kelvin. My temperature is 400 C, which is 673 Kelvin. Well, I got this little diagonal thing happening. And then 740 torr. Well, we've got to put this in ATMs, right? So 740 torr, right? And for every 760 torr equals 1 ATM. And so that's going to equal 0.9737. I'll put that down here. 9737 ATM. All right. And then when I work that out, I get a value of 0.536 liters. Okay, so under a little bit of different conditions, you can see here that the value is a little different than it would be at STP. All right, so there's the first problem. Let's move on to another one. All right, here we have a problem, and this is a little bit brings back a little bit of the memory of last chapter. Concentration of HCl. So let's look at the equation. Is it balanced? It looks balanced. All right. So I need to find the concentration of HCl. Now, if you remember from last chapter, concentration is molarity, and that means moles per liter, right? Well, they've told me right here what the liters of HCl is, but I don't know how many moles of HCl there are, so I've got to find that. Well, look at the conditions they gave me for the gas, carbon dioxide. Now, they don't say the gas, but if you look at the states of matter, that's your only gas. So that gas is in the conditions of 27 liters, 26 degrees Celsius, and 0.925 atmospheres. So if I have all that information, I can find moles. So let's do that. N equals PV over RT. Okay. And the pressure is 0.925 atmospheres. The volume is 27 liters. That's twice I've done that, liters. Okay. R is 0.0821 liter ATM mole K. And that's times the temperature of 26 plus 273, which is 299 K. And so you work that all out, and you get 1.02 moles. Now that's 1.02 moles of CO2, right? And we've got to find the concentration of HCl. So what's the mole ratio between CO2 and HCl? Well, you can see it's a 1-to-1 mole ratio. 1-to-1. And then I'm going to go ahead and let's see what that's going to equal 1.02 moles. And then I'm just going to take the volume of the acid, which was right here, 2.6 liters, and divide by that. And when I do that, I get 0.391 molar. So there's your concentration of HCl, all from gases. All right. One more. Let's see what we got here. Oh boy, look at this. This is one of those limiting reactant problems, it looks like. So they give us, they want to know the mass of H2O, okay? And the thing they give us is they give us the volume of O2 and of NH3 at the same conditions, all right? Now, as you experienced last year, anytime you're given an amount for both reactants, you've got a limiting reactant problem. So what are we going to do? Well, we're going to use those conditions there to find the moles. So let's start with that. So N equals PV over RT. And this is for O2. Okay. So the pressure is 1.25 atm. The volume is 65 liters. 0.821 is my gas constant, and my temperature is 300 K. All right. So when I work that out, I get let's see, I've got 3.30 moles of O2. Okay, so I'm starting out with that for O2. Now the next one, for the number of moles for ammonia, it's exactly the same setup right here, except my volume is going to equal 75 liters. Okay, so without doing all that, the value I got for ammonia was 3.82 moles. Now you should definitely check my math just to make sure I didn't mess it up. But so we've got two amounts there. Now let's look at what the question was. They want to know what mass of H2O. So we might as well go ahead and find the grams of H2O for both reactant, and then like we did last year, the smaller one will be our limiting, and that will give us how much was really produced. So I'm going to take my 3.30 moles of O2, And I'm going to go ahead and do my mole ratio of O2 here to water, right? So for every 5 moles of O2, I'm going to make 6 moles of water. And then for every 1 mole of water, that weighs 18.01 grams. And so with the oxygen I have, I would make 71.3 grams of water. All right? Now let's see how much the ammonia would make if that was my limiting reactant. So I'll take my 3.82 moles. And for every, in this equation, 4 moles of NH3, we get 6 moles of H2O. H2O is 18.01 grams. Okay, and in that one we would generate 103 grams of H2O. All right, so what that means is that we are going to produce 71.3 grams of H2O in this problem. Okay, O2 is my limiting reactant, and that's how many grams of water we would make. Okay, but then look at this question right here. What is the mass of the excess reactant? Well, in order to do that, I've got to figure out how much of my excess, which happens to be my ammonia, how much of that reacted with my O2. So it's a relatively simple setup. I'm going to go like this. 3.3 moles of O2. Again, that's my limiting. Just do a mole ratio between the two reactants. For every 5 moles of O2, I'm going to use 4 moles of ammonia, and that would give me 2.64 moles of ammonia is how much, that's how much I need. Okay? Well, what did I start with? Well, if we look up here, I started with 3.82, right? So 3.82, here, let me use a different color. So if I go 3.82 minus 2.64 moles, I get 1.18 moles is in excess, right? But notice the question says, what's the mass? All right, so I've got to multiply that by the molar mass of ammonia, and 1 mole of ammonia happens to weigh 17.01 grams, and I get a value of 20.1 grams in excess. Okay, so there we go. Kind of quick and dirty, fast version. Hopefully you could follow it. It was a review, but fear not, we will practice this stuff in class, and if you're a little rusty, you'll get a lot better at it, I promise. So see ya.